So today's contents of lecture is shown here. First, introduction, and second, the overview of antenna measurement method, and facility overview. This time I will explain the antenna measurement facility of MJIIT. And next, for the measurement, antenna should be correctly designed. So fundamental knowledge of antenna will be explained. And from number 5, the fundamental consideration in the measurement. First, the feed cable effect antenna, and next is antenna impedance measurement, and 7, antenna radiation characteristics measurement. 8 is a little bit different from antenna itself. This is radar cross section. This measurement is very special for military application. However, in our facility, we have this function, so I would like to explain. And finally, nowadays, small antennas are used in human body application. So at that time, we must make human body phantom and something. So dielectric material fabrication will be shown. And conclusion. Huh? Not working. Oh, previously not shown. Sorry for the attendees. My mistake. You cannot see. Hello?
Yep, now we can see.
Dr. Saidatul,
Yes,
did this
yes.
become okay?
Yeah. Now,
Oh,
now.
sorry. My student helped me now.
Thank you for the student.
And this is content of lecture. Hello? Are you okay?
Okay, doctor, can hear.
Okay, thank you. So content is from 1 to 9 and conclusion. Next, first, the introduction. We antenna researchers are contributing for development of antenna technologies. So important point of developing antenna is obtain correct electromagnetic simulation result for antenna designing. And antenna design is completed by electromagnetic simulation. Next, we move to the stage of measurement. At that time, to obtain correct measurement result is very important. So many things should be taken care. So that is today's main subject. However, first of all, electromagnetic result to obtain correct simulation parameter should be set correctly, and result should be compared with the theoretical concept. This is very important point. So teachers should take care. When a student brings some simulation result, we must judge from the viewpoint of a theoretical concept. So some theoretical concept will be shown later. Next, to obtain the correct measurement method, antenna is set adequately on a turntable or in a phantom. A surrounding effect should be uh, suppressed the surrounding effect field cable and reflecting objects and something. And the importance of measurement in the simulation, simulation model is very limited, very simple. This is fabricated from the known knowledge of us. However, in actual antenna performance, there may be some unknown factors. So by correct measurement, we can expect, we can find new principle of antenna may be discovered. So we are expecting for the measurement results. So correctly measured, we can expect finding new principle. So next is the overview of antenna measurement method. So circuit parameter measurement, input impedance, reflection coefficient, and transmission parameters that can be achieved by vector network analyzer. And near field measurement, this is very convenient by using a planar measurement setup. We can measure electromagnetic distribution and current distribution near the antenna. So from this information, we can judge this antenna is working correctly or not. And based on the near field distribution, we can calculate the radiation pattern of this antenna. And another is cylindrical measurement. Antenna is rotating on the turntable, and the measurement probe is moved in the vertical line. Then we can measure the electric field all around the antenna. So from this, we can also obtain radiation pattern and so on. If the measurement antenna size is very large, so like a mobile base station antenna, this cylindrical near field measurement is very convenient. And far field measurement is the measurement antenna is far from the transmission antenna. This distance meet the far field distance. Then directly measure the antenna radiation pattern. And if two antennas are placed here, transmit and receive radar cross-section can be measured. The final is a compact range. This is same as this situation. However, if and chamber size is not sufficient for the far field, we can achieve the far field distance by this large reflecting antenna. And this is sometimes used for radar cross-section measurement. Here, the target objective of a small sized jet plane. So the Okay, thank you. So today I will explain this circle parameter measurement and using rectangular chamber. So this is a facility overview of MJIT. We have, this is the vector network analyzer, and this is the transmitter, and this is receiver. And these equipment are controlled by this computer. And the measured data is shown here. This is a radio wave measurement setup. And sometimes, and for the radar cross section also use this measurement equipment, and RCS data will be shown here. And this is inside an echo chamber. And this is dielectric measurement equipment. So this is fabricated phantom, and the epsilon and sigma of this phantom can be measured. If this is replaced by seawater, we can measure the dielectric constant of seawater. Many applications measurement can be applied for dielectric material. So specifications of antenna laboratory is shown here. Transmitter is works from 9 kilohertz to 40 gigahertz, and the receiver works 10 kilohertz to 44 gigahertz. And this vector network analyzer works 10 megahertz to 43.5 gigahertz. This 40 gigahertz band is achieved considering the application of 5G mobile frequency range. So this echo chamber can measure the antenna from 300 megahertz to 50 gigahertz. The size is length is 5.6 meter, and width is 2.9, and height is 2.8 meter. So dielectric probe, the dielectric material constant can be measured from 200 megahertz to 20 gigahertz. So this is a facility specifications. So if you have, you'd like to measure this frequency range, you can come and use this facility for your measurement. So near the antenna laboratory, antenna fabrication room is prepared. So some dielectric substrate, many substrate is prepared. And at the next room, we have a phantom fabrication room. The phantom, that is finally explained. This open and a mixer and stock in a refrigerator. And the dielectric constant can be measured by this setup. So I would like to explain the main contents of this lecture. Fundamental knowledge of antenna types, wire antenna, patch antenna, horn antenna, radiation pattern antenna gain, and circular polarization is very interesting, so explain here. So antenna types are categorized: wire antenna, patch antenna, horn antenna, metamaterial structure and array antenna and aperture antenna, reflector and lens. All these antenna can be measured in the laboratory. So depending on the antenna size in aperture antenna or array antenna, the far field distance should be take care. First of all, the fundamental knowledge of wire antenna performance. So wire antenna usually used small size antenna. So fundamental antenna is half wavelength dipole. This is most commonly used antenna. The input impedance is 75 gigahertz, 75 ohm. So this is almost match to the coaxial cable. At 20 gigahertz, the half wave length becomes 7.5 centimeter. So this is very conveniently used for portable radio phone. However, now this size is, if dipole antenna is attached in the handy phone, this size is very large. So some small sized antenna is put inside the handy phone. So if the length is directly short length, then antenna impedance is changed. Very large capacitive reactance appear, and RD radiation power resistance become very small. So in this case, reactance part meaning the stored power, and this real part means the radiation power. So in this situation, stored power is very large and the radiation power is very small. So not suitable for use. So the small antenna meandering this shape, and the total length become more very small, less than 1/10 of wavelengths. By looping the this wire, we can achieve another. This is called normal mode helical antenna, and spiraling also reduce the size. So by meandering, the input impedance become like this. So in meander line, the inductive reactance is appear. So by designing this inductance and the capacitive reactance, we can achieve self-resonance. This reactance part can be cancelled out. We can achieve only the resistance. This looping also capacitive and inductive reactance together exist. So this structure can also produce cancel out the reactance part. This spiraling is also cancel out the reactive part. So by cancelling out this reactive part, we can obtain effective radiation from these structures. So that is a very important characteristics. This is called self-resonant condition. In this case, capacitive reactance and the inductive reactance cancel out. So input impedance become pure resistance. So in this situation, electric and magnetic stored power are cancelled and effective radiation power is achieved. So these structures are very useful in the case of reducing size antenna. So first, the performance of a half wave dipole is shown. Radiation pattern is become like this one. So actual radiation is become this H-shape radiation pattern. The half power beam width become almost 80 degrees, very wide. And the antenna gain become 2.515 dBi, and the input resistance becomes 72 plus J 42.5. So this impedance is shown in this Smith chart. The locus become like this one. So this is resonant point. If this impedance locus is shown in this rectangular coordinate, this L is changing, the resistance increase, and the reactance part become like this one. At half wavelength size, it become this value. A little bit inductive reactance appear. And by reducing the total length, then resistance reduce and the reactance part become capacitive. This part is inductive and this part is capacitive. So in the very small size, very large capacitive and small resistance. That is understand from this L dependence of antenna impedance. So a little bit additional explanation for the small wire antenna that will be used in the embedded antenna in the human body. Meandera antenna impedance is capacitive and inductive, and to cancel out the self-resonant structure is expressed by this equation. W is width and L is this length, and N is the number of turn of meandering. So by this equation, we can find out resonant structure. This horizontal axis is L divided by lambda, and the vertical axis is W, width divided by lambda. So this bold line shows the simulation, and this dotted line is based on this equation. So this equation very much will agree with the simulation result. So this design equation is useful for designing this meander line. Similar for normal mode helical antenna. This is a looping structure. H is the height, and D is the diameter. This I mistake. This H is a horizontal line. the inclination of the curve is different from meander line antenna. No, in the normal mode, the inclination become like this direction. And the length of antenna and the diameter of antenna and the number of turn. So this straight line is this equation, and the dotted line is dotted line is the equation, and this solid line is simulation result. From this very good agreement, we can rely. We can use this self-resonant equation for designing this loop normal mode helical antenna. So these equations are derived by our research group, and based on the exact calculation result of electric field inside and on the surface of the meander line. So to achieve this equation, the correct simulation result very important. So we many times try and error and find out the correct simulation result, and we can finally achieve these structural equations. So for the input impedance measurement, this input, this is the small dipole resistance. This is reactive resistance. This loop or meandering, and RO is ohmic loss of the wire. In this case, the RD and RL value is very small. So this is some example of fabrication of meander line antenna. So original feeding point here, impedance become like this one. It almost 8.9 ohm at the resonant point, or 8 ohm. And in the case of normal mode helical antenna, if we feed here, the input resistance become very small. So in this situation, if we measure the VSWR, this is far from 50 ohm. This also far from 50 ohm. So VSWR become like this one. So we cannot correctly measure the VSWR characteristics of this original antenna. So in the measurement of VSWR, we must step up the input impedance. This also, we must step up the impedance. Then we use this structure, some additional wire is attached. This is called tap feed. For the normal mode helical also attach this tap feed. Then we can achieve the step up of input resistance. This also step up the original input impedance to almost near to 50 ohm. So we can measure the VSWR of original meander and normal, like this one, by attaching tap structure, the correct VSWR is measured, and we can estimate the bandwidth of this antenna. So this is a very important point. If input impedance resistance is very small, we must use tap feed to step up the impedance. Next, the patch antenna performance. Principle of performance. Patch antenna is a patch plate is put on a substrate, and behind is a conducting plate. This is a structure of a patch antenna. So patch antenna works like this one. Inside the substrate, resonant is happening. This is the fundamental performance of patch antenna. In the substrate, resonant electric field is produced. The feature of this electric field distribution, the left side is electric field going to up, and at the center, electric field becomes zero. On the right side, the direction of electric field is inverse direction. This zero, and electric field going down and increasing, moving to the open edge. So the electric field at the open edge becomes the highest. So this distribution corresponds to the size of this size is half wavelengths of inside the wave. From this quarter wavelengths, this quarter wavelengths, so total become half wavelengths. And the wavelengths in the substrate is calculated. This lambda zero is a free space, and lambda g is free space wavelengths is divided by root epsilon r. Epsilon r is the constant of substrate. So to achieve this distribution, we must select the lengths to be half wavelengths in the substrate. And next subject is to find matching to the feed cable. So if feed cable is attached here, the electric field is zero. So the input impedance becomes zero. At the opening plate position, feed is attached. This is very large electric field. So at this point, input impedance becomes 175, very high. So between the opening point and the center, there is a best position for 50 ohm feed. So at this position is selected, then this antenna impedance becomes 50 ohm. So this meet to the coaxial cable impedance. So like this, the feed point is not center and not the opening point, a little bit inside. So for the feeding structure, the coaxial cable can be used, and another feeding method is using the strip line. So in the case of strip line, strip line should be come inside the patch antenna to the feed point. So by achieving this condition and produce resonant and 50 ohm feed, then we this antenna works well. So the radiation is effectively from the opening side, and to achieve the sufficient radiation pattern. So this is electric field distribution. So this electric field corresponds to charge existing. To produce this electric field, here the plus charge is expected to exist. And at this, the electric field coming to the this point, then we can consider minus charge is existing here. So at this H plus charge, at this H minus charge. So current distribution produced in this direction. And current amplitude is at the edge small, and the center of patch, the current become very large. This is the ideal current distribution of this patch antenna. And this is the impedance locus of the patch antenna. If best feed position is selected, this become almost ugly 50 ohm. If this feed is moved to the open side, this come to right side, high impedance. If this feed position is selected near the center, this become move to left side, smaller impedance. By selecting the best position we can achieve, like this, matching to coaxial cable impedance is achieved. This is the fundamental principle. We can understand this principle of patch antenna. Then we can design correctly. The simulation result become like this one. S11 is very small, less than minus 20 dB. And this shows the electric, this is a H field correspond to the electric current. So this is feed point. This probe feed is used. The center part, the strong current produced, and at the edge, the current becomes small. This is the case of strip line feed. The position is same as this, and strip line feed point should be inside, and the similar current distribution. Center part is strong and edge part small. Then, if this situation is achieved, the radiation pattern over like this one, and the maximum radiation gain become 8 dBi. So this is the basic. So from the basic structure is achieved, then some modification of this designing can be proceeded. This is the horn antenna. So horn antenna is not the resonance. So this can be rather easily achieve the performance. The antenna gain is determined by this. The horn diameter is D, then gain is pi D divided by wavelengths of power squared value. So in the case of rectangular horn, gain become 4 pi. A, B, A and B opening size divided by lambda square. And another important gain and beam width. Beam width is this 3 dB down this angle. This is expressed by this one. Wavelengths divided by this diameter. This in this rectangular horn, this is wavelengths divided by this size. This is horn antenna performance. In the case of simulation, it become like this one, the radiation pattern. And this is 3D radiation pattern you can obtain. This is circular horn, and this is a rectangular horn. And for more large antenna, the radiation pattern from a square aperture. And this is similar to the rectangular horn, only the aperture area is shown. This is the fundamental equation to calculate the radiation field of rectangular. This A is this area. So by putting this phase part, that is X direction phase change and Y direction phase change is separately expressed. And this integral can be divided in, converted to X integral and Y integral. So this integral is very simple, exponential jkxu integral by in the X direction integral. So this can be achieved very easily, and the final integral is achieved sine ku Lx divided by 2 ku Lx divided by 2. So this is in the X direction integral, and Y direction integral, this become Ly, and U become V. So finally, radiation pattern is expressed by the size multiply and this part, and X is changed to Y. So this is the X direction radiation pattern, and this is the Y direction radiation pattern. So in the phi equals 0, in this horizontal direction, this k is wave number and expressed by 2 pi divided by lambda. So fx x direction, this x direction radiation pattern become this one, and this part is expressed by x. Then x direction radiation pattern become like this one. Sine x divided by x. This is a very famous function called sinc function or sampling function. So from this function, we can obtain the radiation pattern. Feature of this sinc function, then we can calculate the a half power beam width will be half power angle h theta half power angle is calculated this one. So the beam width can be calculated by using this approximation. Theta b is expressed by 50.8 lambda divided by the x direction aperture length, this one. So from this, we can understand the radiation characteristics of Fx. And in the Fy is also similar to this one. And the beam width sharpness of this beam is determined by the size of x direction, size of x direction, or size of y direction. So for very small aperture antenna, radiation characteristics can be estimated very simply. Beam width. And next, antenna gain. Antenna gain definition is based on this equation. This maximum power density at the antenna. And this part is isotropic power density omega 0. This is isotropic means radiation spread on the sphere of radius r. So this one, applying this one, this part is omega 0. So this part is in the case of directional antenna. So this WP, omega P can be expressed by this equation, and and this also aperture power is expressed by this one. So finally, we obtain putting these values to here. We finally obtain very simple expression of gain. 4 pi S is this aperture area divided by wavelength square. the antenna gain is derived from the definition and putting some power expression and power density expression. We can achieve this simple expression for the gain. So we obtain, so beam width is this equation and the gain is this equation. So we can estimate this is larger than more 2 wavelengths over 10 wavelengths large. We can estimate the beam width and the antenna gain. So another estimation method of antenna gain is based on the radiation pattern. So the radiation pattern integral can be calculated, and the maximum this radiation pattern is put here. Then antenna gain based on the radiation pattern can be calculated by this equation. So circular polarization next. This is the final of the antenna characteristics. So circular polarization is rotating in the direction of propagation. So from this, the polarization is rotating like this one. So generally, this circular polarization is very special case. Generally, the elliptical polarization is achieved. So elliptical is meaning the long axis and the small axis. This is not the same. If long axis and the short axis is the same, it becomes circular polarization. So this elliptical polarization is can be expressed by the combination of the right hand and the left hand rotation circular polarization. This polarization and this polarization. So the one circular is expressed by A, and another polarization is expressed by B. Then cross polarization discrimination is determined by the ratio of A divided by B. So another important parameter for the circular polarization is the axial ratio. Axial ratio is determined by the long axis L and the short axis S. So sometimes circular polarization is characterized by axial ratio 2 dB or something. That is depending on this definition. So this XPD is meaning of right hand circular polarization of the left side circular polarization. If pure best circular polarization is XPD is very large and axial ratio is very small. So in the case of B become very small, the XPD become larger, and the axial ratio is decrease. This is a good circular, and this is a bad circular situation. And this is very elliptical. This is almost pure circular polarization. So that is from this relation of SPD and axial ratio. And in the measurement, if we use the circular polarization antenna here, then the same circular polarization is this one, and the cross circular polarization become like this one. And this difference is XPD. And if we can, we use the dipole antenna rotating here, then this circular polarization characteristics is become like this one. So axial ratio is in any direction, axial ratio is appear. So this rotating of dipole antenna, the ripple appear in the measurement result. This is one measured result of a circular polarized antenna by dipole antenna turning. This is a result of circular polarization antenna measurement. So typical circular polarization antenna are shown here. Cross dipole and axial mode helical antenna, patch antenna with offset feed. So this is most simple structure. Cross dipole is most simple structure. So I explained the performance. So vertical excitation is only at the center, vertical wire and the horizontal wire. If horizontal wire length is a little bit short from the half wavelengths, and the vertical wire is a little bit larger than half wavelengths, then this impedance, vertical antenna impedance become R plus JX, and horizontal wire antenna impedance become R minus JX, minus JX. So by using this impedance, we can calculate electric field in the horizontal direction and the vertical direction. So the finally, horizontal direction is expressed by the length of antenna constant exponential j pi divided by 4, quarter pi. And vertical direction is antenna length and the constant minus j quarter pi. So if this is take a reference, then it become phase is 0. Phase is shifted minus pi divided by 4. So then this should be added minus pi divided by 4. This become half pi. and this phase becomes zero. So comparing these two phases, this vertical excited field become half pi shifted. Half pi degree means 90-degree delay. So these two fields can produce the left rotations elliptical polarization. However, Lx and Ly difference is very small. Almost circular polarization can be achieved by this combination. This is the principle of working, producing circular polarization by this cross dipole. So almost fundamental part is finished. From now, I would like to explain some uh, important point of measurement. So, Dr. Saidatu, if
Yes.
it,
Yes, Prof.
I will give a 5 minutes break for the
Yeah,
end.
yeah, sure.
Okay. So, if there is some question as for the former part, 5 minutes break, I will start from 11:15.
Okay, sure.
Okay. So in this period, I can answer for the questions from the audience.
All right. Okay. Okay. So now we're going to have a take a break for 5 minutes. We're going to continue back at 11:15. For those who have a questions, you may ask your question directly to Yamada Sensei, or you can write down your questions at the chat area, so that he can read the questions. All right. If you have any questions, just maybe just write down the questions at the chat section, and we will continue back at 11:15.
Yes. Hello, Dr. Saidatul.
Yes, Prof?
Shall I start now?
Yes, seems like we don't have any questions. You may proceed the presentation, Prof.
Okay. Shall I continue?
Yes, please.
Okay. Thank you very much, audience. I will start now from chapter 5. From here, that is measurement technology. So first of all, feeder cable effect can be reduced. To feeder cable effect is current leakage. So to suppress this one, balloon structure is useful. And the next impedance mismatch effect will be explained. First, so in the case of feeding by coaxial cable is composed of inner conductor and outer conductor. The current flow inside on the interconnector and the current distribute in the outer conductor. So the antenna is attached like this one. So directly to interconductor and one part of the outer conductor. So the connected part to the interconductor, all current so current amplitude is same as antenna and inner conductor. However, the antenna part attached to the outer conductor, only a part of current flow on the antenna. So the current not same as this side antenna and inter outer conductor side. This current mismatch appear. So this some part of the outer conductor current flow out, and this is called leak current. So this leak current produce bad effect for impedance and the radiation pattern of antenna. So the not the same current flow on this side and this side. So the current difference is appear. This is the simulation result. This is leak current flowing on coaxial cable. And this current amplitude and this current amplitude is different. This is strong current. This is a little bit weak current. The current gap is appear here. However, in the case of this balloon is applied for this coaxial cable, then the leak current become very small. This is light blue. This is dark blue. So current become very small. And the current on the antenna become almost same color. The strength of the difference is very small. So the almost the same current flow on the upper side and the lower side antenna. This is a simulation result. So this shows the designing of a balloon. This structure is called a Schwertop. So this balloon is called Schwertop balloon. So this balloon length is a quarter wavelength. And this is attached to the outside conductor of coaxial cable. And this is soldering. So if this balloon is attached, the impedance from here, there is two parallel line, and the parallel line is quarter wavelengths, and the opposite side is short. Then the impedance become infinite impedance here. So this infinite impedance shut the current flow here. So the leakage current also shut down. Inside, no current. So this leakage current flow is also suppressed. So most of the outer conductor current is guided to the antenna. So by attaching this spirited balloon, the current left side and right side become almost same as the this result. So actually, this is actual case. Here, this is the sphere top. The length is quarter wavelengths. The bottom is soldering. And this is inside the conductor. This part is outside conductor. Attached here. Attached here. So this suppress the leakage current. So this also only the coaxial cable and covered by sphere top balloon. Then current flow on the cable become very suppressed. So in this, if this is a small antenna, the effect is radiation pattern is very serious. So this is a copolar radiation pattern, and this is a cross polarization radiation pattern. So if the balloon is attached, the cross polarization component becomes small. However, without balloon, the cross polarization becomes very large. This is depending on the leakage from the cable. If the measurement antenna is very small, the leakage current from here produce unexpected very large radiation. So we must suppress the leakage current by balloon. This is, in this case, a very serious effect is observed. So to check the leakage current existence, we can use our hand. We put hand, attach hand on the coaxial cable. And in the case of a balloon, we attach our hand to coaxial cable. Balloon. If there is a leakage current, the measured data is moved by attaching our hand. However, with balloon case, if we attach the balloon, this impedance locus cannot move. With balloon, no move. And without balloon, the impedance locus move. So we can check the effect of the leakage by watching the impedance and touching our finger to the leakage part. So this is a very easy checking point, and we can use our body to check the performance of the antenna. So next is the reflection. The impedance mismatch is happened here. Then reflection produced. If the difference of input impedance and the cable impedance is large, this is this ratio. So this part is mismatch is very large. Then the reflection power become large and the input power loss become large. In this case, no mismatch, so no power loss happens. The power loss is calculated by this equation. Next is the antenna impedance measurement. The principle of a vector network analyzer and calibration method, checkpoint of measurement, transmission parameters. So this is a vector network analyzer in one port, and the test antenna is attached. So the principle of VNA is measurement of reflection from the measured antenna. So the reflection wave is converted to amplitude value and the phase value. So the amplitude value and the phase value is expressed in the Smith chart, like this one. This radius is amplitude, and this angle is phase. So the measured data is shown on the Smith chart. And Smith chart express the real part, resistance part, like this one. And this is reactance part. All the value is normalized by the impedance of the cable. At this point, the reflection amplitude is 0. So no reflection. This is good position for matching. So from this R equal 1, R is divided by the impedance. At this point, the antenna impedance becomes same as the feed impedance. If that is 50 ohm, this point become 50. And this point become 25 ohm. This is 10 ohm. This is 0 ohm. And this is increasing. And this circle shows the reactance. This plus reactance is inductance. This minus X is capacitance. So at this point, we can determine the input impedance from the point. This is the principle. Vector network analyzer measure reflection and the amplitude and phase are shown on the Mismatch display. So from this point, we can calculate the input impedance. So at first, we must calibrate by using the calibration kit. So by putting here the short, it become here, open here, and dummy here. So this is the calibration point and calibration finish. This is the reflection display. Short and open become here, and dummy become very small reflection. And one important point is if test antenna is feeded by some length of feed cable, so we must use the same length cable, adjust cable for the calibration measurement. Without this adjust cable, the measurement locus become rotate by the lengths, this feed cable lengths. So in the case of calibration, we must use adjust cable, the same length with the feed cable. So another checking point of antenna radiation. If antenna working, then there is a current flow on the wire. So by touching our hand, the current flow on the antenna is changed. So in this case, impedance movement by our touching, that is good. By touching the antenna, the current distribution is disturbed. So the impedance is changed. In this case, antenna is sufficiently working and the current flow on the antenna is correct. Without movement, then the current flow on the antenna is not sufficient. So some soldering or some mistake is happened in the antenna connection. So from the measurement data, if the impedance locus move by attaching hand, that is antenna is working. So like this one, from the measurement impedance, attach antenna, then move is okay. And attach feed cable, move is no good. Like this one, our body can be used to check the antenna performance. And next is the transmission parameter. So S11 and S21 can be measured by vector network analyzer. S21 is from this port to this port. So amplitude is okay. However, in the case of phase measurement, in the calibration, the same length of cable should be attached for the calibration. If the calibration cable is not used in the calibration, the phase become like this one. Very sawtooth shapes phase different will be appear. In the case, the test circuit is larger compared to the wavelengths. So if we calibrate with the calibration cable, that length is almost same as the circuit size. Then the measured data become like this one, smooth data of phase difference. This phase difference is originally like this one. So we, in the case of phase calibration, the calibration cable, the size is same as the circuit should be used. So this is not correct calibration. This sawtooth phase is appear. However, in this case, successful. The calibration in case the calibration cable is attached, then the measured data become like this one. Good phase measurement can be achieved. So next is antenna radiation pattern, far field condition, test antenna setting condition, measurement equipment, measured example. So the far field condition is given by 2D. D is the antenna size. 2D square divided by wavelengths. So the test antenna should be placed on the center of the turntable. And for the checking point of the antenna is we cover by our hand the antenna. Then if the impedance locus move, then this antenna is working. So by the covering our hand, radiation is condition change, so impedance is moved. In the case of movement, the antenna is radiating sufficiently. However, no move, the antenna is not radiating. So this in our facility, there are many horns for the measurement. 300 mega to 2 gigahertz long peri, and reach horn is 1 to 18. And 4 millimeter, 26.5 to 40 gigahertz. By using this one, we can measure some test antenna and obtain radiation pattern. And for antenna gain, some reference standard dipole antenna is used. This is standard dipole and test antenna. So the measured gain is the difference. So time is limited. So radar cross-section measurement is shortly explained. Radar cross-section is like this one. The illuminate the target and the diffraction from the target. This is ratio is radar cross-section. By using radar cross-section, the received power is calculated by this radar equation. And radar cross-section is some special expression. The radar cross-section of this square area S is expressed 2 pi s square divided by lambda square. And in the case of sphere, this is very simple. Cross-sectional area pi a square. This becomes the radar cross-section. This shows the example of calculation of received power. So in the practical measurement, radar cross-section is a measure. So, however, in the measurement, transmission horn and receive horn are very closely setting. So coupling from the transmit horn to the received horn, that is produce very serious problem. However, by using time domain function, we can cut the coupling. This is the frequency sweep radiation. Then that is converted by time domain. Then this swept frequency is by time domain. There is a pulse shape. So this pulse width is expressed by the shift sweep frequency inverse of the sweep frequency become the pulse width. So in the case of sweep frequency width of 7 megahertz, the pulse width become 0.14 nanosecond, very short pulse. So by using window function, we can select only this. This is the target. This is from the coupling by neighboring horn, transmission horn. So by selecting this one, this effect is cancelled. And another reflection component can be cancelled. Only the target reflection can be measured. So some measurement process is shown. And this is the target is selected, very typical part. This cone and this cylinder and this hemisphere. Then we can obtain. So our obtained data is received power. However, received power should be converted to radar cross-section value. That is some calibration measurement is needed. The relating to the received power and the radar cross-section. In this case, the received power of minus 40 dBm correspond to the radar cross-section of 20 dB square meter. So the target setting is very serious. And this is obtained data. This red line shows the measured result, and dotted blue line is simulation. Almost a good agreement of measurement. This is the back area, almost constant level achieved. And the side area is very strong. And this is this area. And this head is this taper reflection. Radar cross section become very small. So the correct characteristics can be measured. So my part of antenna measurement is finished. From now, Dr. Kamilia will explain the dielectric material fabrication.
All right, thank you, Professor Yamada Sensei. Now we proceed with our second speaker, IR Dr. Kamilia. Please welcome.
Yes.
Okay, Assalamualaikum and good afternoon, everyone. So I will continue for the last chapter of the talk today. We're going to explain about the dielectric material fabrication. Right. So we will discuss about the chemical materials for human body phantom and the fabrication process of the human body phantom, and finally the dielectric constant measurement. Okay, so basically in our laboratory at MJIT UTM Kuala Lumpur, one of the research that we embark is the implantable antenna for biomedical application. So basically the concept is to have the antenna inside the human body, and then wirelessly external reader will capture the signal, and then the medical practitioner can receive the vital values from the devices. So basically, in general, for human healthcare, the biomedical telemetry device, we divided we divide it into three, where one is for wearable, for example, for insulin pumps application. And then another one is implantable, for example, for pacemaker application. And the third one is the ingestible application, where we can use it for capsule endoscopy. So in order to realize this in research point of view, we have to fabricate or maybe we have to mimic the human body tissues. So basically, this is the general setup for the antenna inside a human body phantom. So this is the human body phantom that we have fabricated, and we put the antenna, the small antenna, inside this, and we measure the values using a vector network analyzer. Okay, so basically in order to do that, we have to have the ingredients for the chemical materials for the human body phantom that we would like to investigate. So for example, so this is a published values from the literature for the many biological tissue. So this phantom, it is dependent on the type of biological tissues as well as the frequency. So for example, for this tissues here, muscle, the permittivity should be around 58.8, and the conductivity should be around 0.84 with a mass density of 104. And for stomach, the permittivity should be around 67.5 with a conductivity 1 and mass density 1.05. Okay, so the materials that we use for the to realize this muscle and stomach phantom is deionized water, polyethylene powder, agar, sodium chloride, thickener, TX151, or we can also use a food grade xanthan gum, and as well as sodium dihydroacetate. So basically, this polyethylene powder is very important ingredient. This will determine the value of the permittivity, this value here. And the other very important chemical materials is the sodium chloride, where this will very much affecting the conductivity values. So from our research, this is the ingredient that we have researched on, the recipe that can give the values of the required permittivity and conductivity for muscle and stomach in order to mimic the actual body tissues. Okay, so basically the fabrication process, there are a couple of steps. So the first step is to prepare, to weight and prepare all the required chemical substance, and also to prepare the mold to put the phantom. So again, we have the deionized water, the agar, the sodium dihydroacetate, the polyethylene, sodium chloride, and the TX151, or we can use xanthan gum. Okay, so the next step is to combine the deionized water and agar to be put inside a pot and stir it well. And the third step is to insert the sodium chloride and sodium dihydroacetate in the previous solution and stir it until well combined. And the next step is to cook the solution with a low heat until it becomes transparent, and the solution has to be ensured not to be scorched. Okay, so we have to use a very low heat of fire. And the fifth step is for the cooker to be turned off, and we will add bit by bit the thickener powder and use a mixture to mix well the solution. And the sixth step is to insert the polyethylene powder, the material that determine the permittivity value, and mix it well with a mixer. Okay, so once we already have this solution, we have to pour it inside a mold or a container, and we have to be very careful to ensure that there is no bubble to be formed in this step. And then we will have to put this inside a refrigerator to harden this phantom. And then the next step is the measurement of the dielectric constant. So to be able to check the electrical properties of ER, conductivity, tangent loss, whether the fabricated phantom really mimics the tissues or not. Okay, so this is the photos of what we did at our laboratory. So we have the chemicals prepared and weighed. And then we will mix the solution, the chemicals, and also use the inductor to heat it. And we have the mixer to make sure it mix well. And once we have a good solution, we will put it inside a mold container. And so we have this, and we put it inside the refrigerator, and we will get a nice phantom, and then we can start to measure the values of the permittivity and conductivity. Okay, so this is another fabricated human skin phantom that we have fabricated. So these are the recipe that we have done in our laboratory. So this is for skin. All right. Okay. So this is the next is dielectric constant measurement. So in order to ensure that the phantom really mimics the biological tissue, for example, if you want to have a fat or a stomach or muscle, we have to measure the dielectric properties. So the equipment that we use is the vector network analyzer with a dielectric measurement probe. This is a probe, and we will have a probe stand and a cable. Okay, so basically the concept is to have a vector network analyzer with an open-ended coaxial probe. This is a coaxial probe. So the software will controls the VNA to calibrate the instrument and then to perform the measurement, calculate and display the results. So to measure, we will put this tip of the probe and press it on top of the solid sample or immerse it into a liquid sample. So this technique can be used for solid as well as liquid. Okay, so before we do the measurement, we need to do the calibration. So we need to calibrate it with air calibration, short calibration, as well as water. And then we can start measuring the permittivity, loss tangent, and the material. So this is air calibration, short calibration, water calibration, and this is the steps of actually measure the sample. Okay, so for air, the permittivity of air is 1. So we have to ensure that we get this value when we measure so that it will be calibrated. Similar as water, we put a deionized water and we should be able to receive the properties of ER dash around 79 to 80. So this is indicating that this is calibrated, and we also have to calibrate for short. Okay. So and then we can proceed with the measurement of the sample. For example, this is a human body phantom. So so this is the value of E dash, okay, at the 402 megahertz. So we receive value around maybe 12 there. Okay, yeah. Okay, and then basically the measured value will be E dash and E double dash. So for the conductivity, we can get the value using this expression here. So from the E double dash, we can get the conductivity values at the specific frequency. We can also measure the textile material for this using this dielectric probe, and any other material, like for example your substrate. Okay, maybe you build your own substrate and you want to do this, you can do that as well. So for example, this fleece, we measure and it's around 1.2 to 1.6 permittivity with the loss tangent 0 up to 0.05. Okay, so this is for textile material. So we have a published theoretical material values of permittivity and loss tangent, and then we actually do the measurement in the laboratory and try to see whether the value match or not. And fortunately, the measured values reasonably match between the theoretical and published data. So that's how we do the dielectric probe measurement to measure the dielectric properties of body phantom, textile, or any other substrate that we would like to see. Oh, and another thing, we also measure the properties of seawater, because we also do research for seawater antenna with a underwater. So we do that also, but I didn't share the result here. Okay, so the conclusion for today's lecture by Prof. Yamada and myself is first, important measurement technologies have been very well summarized by Prof. Yamada earlier. And he also talked about the leakage current to the feed cable that need to be suppressed. And in antenna measurement, we need to check the antenna working by using our body actions. And from measurement, unexpected antenna principle may be discovered. So that's why sometimes we do not actually get the similar result with the simulation. So we have to do a couple of times of measurements because there might be some losses and whatnot from our setup. Another thing, the equipment for antenna measurement is very sensitive, so we have to be careful for the connector setting, cable condition, and so whatnot. Right. So before we end this lecture, this is our laboratory at MJIT. This antenna lab is at the building of wireless center communication at UTM Kuala Lumpur. This is together with MJIT, and then this is the MJIT building. So we are located at UTM Kuala Lumpur, Jalan Sultan Yayat Petra, 54,100 Kuala Lumpur. So if you have any question, you can just email Prof. Yamada or myself, and this is our website. And we welcome any request for lab visit, a lab tour and whatnot. And we also offer requests for antenna measurements at our laboratory, but with some fees. So that's all from us, Dr. Sadakul.
Right, thank you very much, IR Dr. Kamilia and Professor Yamada Sensei. So now I open up the floor for any question. Okay, any question from members of the floor? I may ask directly questions to our Professor Yamada Sensei, and you can also ask about the measurement technique to IR Dr. Kamilia. Any question? Dr. Kamilia, if we wanted to go visit to
Yes.
the lab,
Yes.
I mean, like, do we need to make an appointment first? And how much is the cost?
No, for visit is free. You can just make appointment through me or Prof. Yamada. Visit is free, but for measurement there is some fees lah. But you can communicate through the email lah for that.
Okay.
Hello, Prof. Yamada. I
Yes.
have one question. Hi, this is
Thank you.
Tarikul. How are you, Prof?
Oh,
Yamada?
fine. Thank you
Yes,
very much.
yes, yes. Okay, it is interesting talk, really, and you enlighten us a lot of measurement inside. Just curious to know that in reality, for high frequency measurement, like for example, 38 gigahertz or 28 gigahertz, are you taking any separate precaution before you start in real example? Any issues you face during the measurement procedure?
What measurement? I cannot hear.
Far field measurement, 28 gigahertz.
Far field. Yes, we can. So now we are trying the measurement of lens antenna working at 28 gigahertz.
All right.
So antenna size is 20 centimeter. So the far field distance is around 7 meter, a little bit larger than the size of the anechoic chamber. So we managed to set the feed horn outside the door, and we managed to achieve the far field distance. So for the preparation of measurement, far field distance is not sufficient. We can reduce the measurement distance almost half. Then the measurement error may be increased. However, for the main beam measurement, no problem. So that is a consideration for measurement,
Okay.
high frequency and large antenna size.
What about the efficiency measurement? Gain. Are you predicting that with
Yes,
this
gain measurement is done compared with the standard gain horn.
All right.
So if you would like to measure more than 28 gigahertz, our facilities are able to measure up to 40 gigahertz. So if you would like to use, we welcome.
Thank you. Thank you, Prof. Yamada.
Thank you.
Thank you very much.
All right, thank you, Professor Toriko. We have one question at the chat. It says that during measurement of patch antenna, how to test the antenna is working well by the current flow and no short circuit? What does it mean?
Are you question to me?
Yeah, there's a question. Sorry, there's a question in call messages. So I just read out the question.
What question? Once more, please.
Okay.
Repeat.
Siti Zainab asks, during measurement of patch antenna, how to test the antenna? Is it working well by looking at the current flow and no short circuit?
So touching the patch antenna itself, if we touch no impedance change, the current is not sufficiently flow on the patch. So if measured impedance is not correct, then the connector may be not working. The soldering the connection of the antenna and the feed cable may be some mistake. So soldering technology is very difficult. So the student sometimes put solder on the metallic plate. However, that is not completely connecting, only touching. So to sufficient soldering, the antenna and the solder should be warm up sufficiently and make clean the surface. So if that is not sufficiently prepared, soldering cannot achieve well. So sometimes no correct soldering is not achieved. So that may be a main problem in the patch antenna measure case.
Yes. Oh, okay. There is one more question, last one, okay, because we ran out of time. From Saif Hanan. Is there any effect of metasurface placed on the surface of the substrate of a patch antenna at higher frequency, say at 28 gigahertz?
Metasurface,
Mm-mm.
metasurface is metamaterial measurement. May be possible. However, we have no experience of metasurface. So that way, in the field of Dr. Kamilia, you have some suggestion?
Actually, I haven't done on 28 gigahertz, so I also have no experience in this. I'm sorry.
However, if uh, they would like to measure metasurface, you can bring in our lab and together with us
Yes.
trying measurement.
Yes, I think for this, it has to be done in the simulator first, and if it's work, we can check. So the effect and whatnot need to be experimented lah, to be measured. I think. Yeah.
Yep,
But
correct.
at the moment, we have yet to embark in this field at this point of time. Not yet.
All right. Okay. Um. Okay. I can. Okay. We are actually running out of time. But there is actually one question from Nurul Haslina. She's asking, is there any tips to minimize measurements and simulation discrepancy? Is there any tips to minimize?
Tip. So some guidance, convenient guidance. So not yet. However, if necessary, we can make tip some guidance to quick checking the correctness of the simulation result. So that is depending on the simulator.
Correct.
CST is some tip. And another simulator, FDTD method, and method of moment, FECO. Many tips, simulation condition, take care point is different. So from now, our IEEE member collect some tips from member side and collect in your part for CST tip and for PECO simulation tip and FDTD simulation tip. That is a very important work in service in IEEE Malaysian chapter for simulator users. So from now, we make some effort to collect some information from simulator users and collect at your side and make some user guide. That is very good products of IEEE.
Nice, nice. Okay, last but not least, can we take a group photo, everyone? For our memories. Okay, so I would like all of you to turn on your your webcam so that we can take a group photo. All right, nice. Okay. I can see Dr. Azrami there. Okay, more and more. All right. Okay, everyone say peace. Where is it? Hang on, yeah. 1, 2, 3. All right. Okay, I think that's all for our today webinar. See you guys again maybe next month. Next month is Ramadan, perhaps next month. Okay. And for that, thank you so much, Professor Yamada Sensei, and also IR Dr. Kamilia, for your time. Be with us today to share your knowledge with us in this webinar. Thank you so much, and see you guys again.
Okay, thank you. Bye.
Thank you. Bye bye.
Thank you, Professor. Thanks.
Oh, thank you.
Thank you, IEEE for inviting. Thank you.
You're welcome.
Thank you very much. We were waiting your visit to our labo.
Oh yeah, yeah,
Yes,
yeah.
Professor Ratul, you are most welcome.
Okay, okay.